Hello everyone. We're going to start now to talk about generative techniques. So these are techniques that take low-dimensional representations of data, just a few numbers, and somehow create these amazing synthetic, much higher resolution things, like fake cats or what have you. So we've already done kind of a warm-up for this in the last assignment. This is where I had you create, actually from scratch, a multi-layer perceptron that implemented an autoencoder. So this was an architecture that took in a digit, in this case 28 by 28, or 784 pixels, and then went through a successive series of layers, going to lower and lower dimensions until finally the encoder got down to only 2 dimensions, only 2 numbers that somehow represented the input. And so that was what the encoder did, and then the decoder went back up, so it went from 2 dimensions jumped up to 128, then to 256, then to 512, and then finally back up to the original resolution. And the idea was somehow that we were able to capture with these, by forcing the network to actually go through this bottleneck in the middle with only 2 dimensions. We were able to force the network to learn a compressed representation of the data. So instead of having to represent this digit with 784 dimensions, which is very inefficient, right? I mean, you know, I should be able to know actually just from a few pixels what this digit would likely be, right? So I'm having the network learn just a couple of dimensions to describe the digit. Now, this ended up not being perfect in our architecture, but this is a good start, and we were able to do it completely from scratch. So when we look at this, the dimensions in this compressed representation, called the latent space, we start to get an idea of how we might be able to use this to generate higher resolution data. So that's what the decoder is doing in this case. So I showed you when you trained this, here's where the training data goes in that space. So luckily, you know, the architecture we chose actually was able to kind of separate out the different digits only using 2 dimensions. But then what I can do is I can actually go into that space and say, all right, well, let me just plop down a dot anywhere and take those 2 coordinates and just put it through the decoder. So now it doesn't necessarily have to have been something from the training data, but I can take something out of sample, something I never saw before. And so, okay, you plop it down there, what do you get? Plop it down there, you get something in between like a 0 and a 6. Now I'm getting something between a 3 and a 9. So these may not be things that probably aren't things that were in the training data. And so if I do a good enough job, I can sort of capture something about the distribution that allows me to generate things that I've never seen before, rather than just memorizing the things in my training data. So that's the idea behind generative techniques. Now, one of the drawbacks of what we've done so far is you see we're not completely filling out this latent space here. We have some gaps, and actually in this case, when I go through the gaps, it kind of looks like it's in between some of those digits, which is interesting. So one of the things that I'm going to really think about in these next few videos is how can I organize this latent space better and really pack things in there so that there aren't gaps like this, and also so that if I move my dot a little bit, I don't suddenly jump from one thing to the other. So that's what we'll talk about. But before we get into that, I actually want to use the same sort of technique with this autoencoder, but I want to use a different architecture. So I'm going to go back to convolutional architectures that we talked about before, which are great for images or other data that has some spatial coherence. And I want to use those instead of multi-layer perceptrons to implement the encoders and the decoders. So that's what we're going to do first, just to review that stuff, and rather than doing it ourselves from scratch, using NumPy, I'm going to go back into Torch because these architectures are going to get a little more complicated, and so I'll just use Torch's implementation of them. Alright, so I'm back in Torch here, and actually, you know, to make us independent of Torch before, I set up digits in my own images, but I'm going to copy and paste some code in here because Torch actually has this digits data set baked into it. So what I'm doing here is I'm going to take the Torch MNIST dataset, that's what it's called. I'll take the training and the test data. Actually, I'll probably just use the training data for now. But yeah, so I can pull that out, and the other thing I can do is use this Torch Vision library to do some transformations to these digits. So it'll be convenient for me actually for the dimension of the digits to be a power of 2 rather than 28 by 28, which is not a power of 2. So I'm actually going to pad these digits on either side by 2. So they started off 28 by 28, but I'm going to put 2 pixels on the left and the right on the top and the bottom, turn those into 32 by 32, and then I'm going to put them into Torch tensors. So, and then maybe I'll store up. So I guess I forgot to download the digits before I started this. Okay, but you'll see if you do it on your computer, it'll download them. So I guess Torch just has a pointer to where these actually are. Anyway, so let me go ahead and pull out the first digit and see what it looks like. So if I go data train at index 0, I get back a tensor. Actually, I get back two things. I get the tensor representing the image, and I also get back the identity, the label. Now, we're not actually going to use the labels here because we're going to do something unsupervised. But, oops, I just meant to say that. But let me, yeah, I'll unpack both of these anyway. So supposedly the first example is a 5. So if I print y, I see 5 there. Let's look at the shape of this thing I got out. So interestingly, it actually puts on an extra dimension here. Because actually Torch will always store images as number of channels by height by width. So in this case, it's a grayscale image, so it starts off with just a single channel. But then we end up having 32 rows and 32 columns. So if I were to go look at this, maybe I'll just take out, I'll just slice out. I'll say, okay, yeah, I just want to take out the first channel. There's only one of them anyway. I'll take all the rows, all the columns, and there I see that image 5. And because this really represents grayscale, I can go ahead and say CMAP equals gray. And then I get that there's the digit. So that was a 5, as promised, or at least appears to be. All right. So what I want to do, of course, I could flatten this into 32 squared or 1024 dimensions instead of 768 or 784 like I was doing before. But now I want to use a different kind of architecture. I actually want to start to use this convolutional architecture. Okay, now if you go back to the schedule, you'll see at the beginning of Unit 4 that I had a link to this live 2D convolutional demo by Victor Powell. So if you are rusty on the stuff, go back here and review this. And remember, what we're doing with a convolutional kernel is this so-called weight sharing. So what we have is this kernel here, which is something that we slide across an entire image. Now the weights here stay the same. So in this case, I'm using something called a sharpened kernel, which has the weights 0, -1, 0, -1, 5, -1, 0, -1, 0. And those stay the same. And so that's called weight sharing. So I slide this thing across the entire image, and I do a weighted sum of all the pixels in a neighborhood around the original pixel that's equal to the size of the kernel. And I do a weighted sum according to those weights that I define there. And then I get the output image, which is the result of applying that to every pixel in this case, sliding this over. Now, like anything in neural nets, what we're going to do is make these weights learnable. So rather than just fixing them ahead of time at this, here was a sharpen, here was a blur, here is what they call a bottom sobel, which picks up on horizontal edges. Instead of fixing like this, we're going to say, I'm not really sure what the best filters are. I'm going to make those variables that I learn. And depending on whatever I want to learn, in this case, an autoencoder. So let me show you how to start initializing a bunch of those kernels that we can apply. So what I'll say here is, so my first layer will be NN. So I've imported this library NN from Torch, which is used to make layers. So nn.conv2d. And actually, let me look at the documentation real quick before I start writing that. So if I say nn.conv2d ? In here, it'll bring up some documentation. So the first thing I want to know is how many channels are there in the input. In this case, it's 1. I'm starting off with a grayscale image. Then it asks me how many channels are there in the output. Well, that's how many kernels I'm going to use. So each kernel is a different channel. So you could have, if you were going to fix the weights ahead of time, you could have a right sobel channel, maybe you had a blur channel, maybe you had a bottom sobel channel. And so that would be 3 channels, right? Each of those different sets of weights is a different channel. So that's what it means for the out channels. Kernel size is the number of pixels I take in each dimension. So here it was 3 by 3. That's a pretty standard choice. I think I'll stick with that. Stride is I can actually skip things as I go. I can go every other pixel. I don't have to go every pixel here. I can actually jump 2 before I get the next one. Jump another 2. Jump another 2, right? So that's called the stride. And then there's other parameters here. I won't get into them too much. padding is just what you end up doing on either side of this if it goes out of bounds. So a padding of 1 would say, okay, I'm going to allow you to pretend that there's like zeros on the other side or something, so I can actually know what to do when I'm at the edge of the image. Otherwise, the output's going to be smaller than the input because I can't actually move this over anymore. That's the idea. All right, so let me just get started with this. I will say, let's make a layer that has one input channel. It has, let's start with, I don't know, like I said, 3 output channels. Kernel size, make it 3. And then I'll say that the stride is 2, so I should expect an image which is half the resolution because I'm going to jump these kernels but over every other pixel. And then I'll pad by 1, just so that I have a 3x3 kernel. I know if I put that kernel at the edge of the image that I'm going to be out of bounds by 1. So let me pretend that I've padded this image by 1. So that's a layer. So I should be able to define that there. What did it say? Oh, it's not pad, it's padding. Okay, so let's do padding. And now if I take that digit image and I send it through, I'll say maybe x1 is equal to layer 1. Doing a forward evaluation on an x, let's see what I get. So if I print x1.shape, cool, it's exactly as I promised. I have the result of 3 different channels, so 3 different kernels, applied hopping, by a stride of 2, so I only take every other pixel. So I go from a 32x32 image to a 16x16. Just to look at it, let's see what it ends up being. It's going to randomly initialize the weights here. So these are going to be like noise, the kernels. Let's see what actually happens when we slide some noise past this. So if I were to say x1 at channel 0, didn't like that because, let's see. Yeah, okay, because technically this layer is differentiable, so what I need to do is take it out of gradient mode first. Okay, anyway. So this was just a noisy kernel, and we ended up with a noisy looking 5. And so these are going to be different noisy things. But we're going to put them through gradient descent and learn something more useful. All right, but before we do that, let's go one level deeper here. So usually you stack these things and you keep going deeper and deeper, and you'll add additional channels and make the images lower and lower resolution. So, and actually, let me change this out channels to a power of 2. So it's pretty typical to actually use powers of 2 here. And okay, cool. So if I look at this, I have 16 channels on the output. So 16 different images, each of which is 16 by 16. A lot of 16s there. Okay. So let me make another layer here. And this layer is going to take on input 16 channels, right? So whatever came out of the last layer. And let's say I output 32 channels. And so check yourself here and see if I were to send x1 now, so the output of layer 1, as the input of layer 2. Check yourself on what the shape of that would be. So pause for a second, see if you can think of what it is. Now if I run this code, I see it's 32 by 8 by 8. And that's because I have 32 output channels. In other words, I'm learning 32 different kernels, but I've strided them when I applied them to the image, and I've done this convolution. I've strided them by 2, so my outputs are downsampled by a factor of 2, just like they were in the first layer. So I've kept that stride at 2. So every time I go, I have the resolution of my images. Okay, but so another thing I'm going to show you here is what is up with the weights actually. What do the weights look like? So if I were to say the following, for weights in layer 2.parameters, and I were just to print the weights.shape. So I commented this out so I can just see the weights here. So I notice there are 2 sets of weights here. The first set is a tensor which is 32 by 16 by 3 by 3. So what I have in this second layer here is 32 different kernels, each of which is a 16 by 3 by 3 tensor. So here's where it gets a little bit interesting. I just want to check to make sure you understand this. In the original example I gave, I only had 1 output channel. And so I only needed, this one kernel here. And that kernel only had 1 input channel. So I only needed weights for 1 input channel here. So it was just a 3 by 3 by 1, or actually in Torch's ordering. This was just a 1 by 3 by 3 set of weights. But as I go deeper, I actually have 16 input channels to this layer. And so for each kernel, so for each of these 32 kernels, I actually need 16 3 by 3 sets of weights. So I need a set of weights for every input channel for every kernel. So I'm going to have one of these 3 by 3 things for every input channel for every kernel. So that's how many weights I have. So 32 by 16 by 3 by 3. Now what is this here? What's this other thing hanging off here? Well, we always have the option to add a bias as well, just like we did with a perceptron. So if I go back and I look at the documentation again, I'll see that there is an option to disable this. So if I were to say bias equals false, then I wouldn't have that extra thing. So sometimes you might want to disable the bias for various reasons, but I'll keep it in there for now as a learnable parameter. Okay, but I'm seeing a lot of repetition here, so it'd be nice to put that in a loop. And so let me make a list that I'll append to as I go through here. And I'll keep track of the number of channels that were into this layer and the number of channels that should be going out of this layer. So it starts off with 1 channel in, 32 channels out. And then I will also keep track, just a couple other things that I want to remember. You know, the dimension of the digit is 32. And I'll be going down to a latent space too, so let me also remember that the dim latent, that I'm going to do just like I did here. I'm going to eventually go down to just 2 dimensions. And I might be forgetting something, but we'll see. Oh yeah, of course, I also want the depth. So this is how many layers, how many convolutional layers I want, because we're doing a deep convolutional network here. So yeah, let me try to replicate this sort of thing, but in a more flexible manner in a loop, since I keep kind of doing the same thing. So I'll say for I in range depth. I'll say layers.append, and let me just copy and paste this, but just change it a little bit. And here's where I have that funny thing in Python where I actually have the named parameter equal to my local variable. So I just want to pass in that variable now instead of the hard-coded thing. But I'll keep the kernel size at 3, and I'll keep the stride at 2 and padding at 1. That makes sure that every time I'm downsampling the image resolution by a factor of 2. And so that's the reason I really wanted to start with the 32 by 32 digit, because that's just a bunch of 2s. So I know I'll always be evenly divisible for quite a long depth. The other thing I want to do here is let me, in addition to the convolutional layer each time, let me also add a ReLU, or some other kind of maybe leaky ReLU, as a nonlinear layer, because this is what gives the neural network its power. Like linear layers, convolutional layers are also linear. What it means is if I superimpose 2 inputs, that's the same as if I had run the convolution individually on each one and superimposed the output. But that turns out to limit, just having linear layers limits the capability of learning. And so we're going to add the leaky ReLU as well. Okay, so let's see how we're doing so far. What I'll do is I will wrap these layers into a sequential model in Torch. And so what this does, this just unpacks all the layers into individual parameters. So it's as if I called this method with 6 different parameters for the 6 layers here. So 3 convolutional layers followed by 3 leaky ReLUs. And yeah, let's see what happens when I apply this. If I say x out is equal to, now I might be mangling this a little bit, so let me just make sure I always reload it down here. So I'll load the x, I don't care about the output, I'm doing an autoencoder, it's unsupervised. So if I were to say x out is equal to layers x, it didn't like that. Oh, because I need to be expanding the number of channels each time. So actually I should say, hey, the number of channels into the next layer is the number of channels that came out of this layer. And then I'm going to make sure that the next time I double the number of channels that come out. Okay, now we're good. So let's see. The output here should have 128 channels. And yeah, I went through a depth of 3. And so I divided the resolution of the original image, which is 32, by 2 to the third. So I divided by 2 3 times. 32 over 8 in that case is 4. let's just go one deeper here. Let's say I added just one more layer then I would be 256 by 2 by 2. So actually quite small images there. And actually, I think I was a little bit inconsistent here. I wanted this to be 16 channels to start with. Okay, fine. Good, all right, so anyway, I have a 128 by 2 by 2 thing on the output. So I want to keep going though, and eventually I want to flatten to something two-dimensional. Now, here I actually have a bunch of dimensions here. And so I somehow need to flatten those dimensions down to 1. And actually, there's even another thing I want to do real quick. I want to say x is equal to x dot unsqueeze 0. So what this is going to do, let me just show you real quick. I also want a batch dimension, because eventually I'm going to send through a bunch of batches of images through here. So really what we want to have is 4 dimensions for our tensor, because we want to have batches all wrapped into one. So this will, now instead of just being num channels by height by width, I'm going to have num batches by num channels by height by width. So here we're just taking out one example, so just one batch. So it's kind of a dummy dimension, but it's to keep the shape. And so anyway, so the output shape is going to be one batch, 128 channels, and of 2 by 2 images resulting. All right, so what I want to do is flatten this last 3 layers here for the whole batch. I have 128 by 2 by 2. I want that to be 1 dimension, because eventually, you know, I want to send that 1 dimension down to 2 numbers. So what I'll do here is I'll say, all right, layers, or I'll just say, just to show you what this looks like, flat equals nn.flatten. So that's a layer. And if I were now to say x out equals x is equal to flash x out and print the shape, what I would get is 512. So it flattened these 3 dimensions into 1. So it stacked them, these 4 groups of 128 on top of each other to get 512. And so now what I can do is go through a linear layer. Now actually it's probably helpful to, so let me say here, this is layers model. I don't love these magic numbers, so let me see if I can remember what this is. So let me try to remember this 128 by 2 by 2 and also this 512. So maybe I'll have this variable. I'll just say before I flatten, I'll say shape is equal to x out dot shape, and I don't care about the batch dimension, but I do care about the number of channels and all that. So let me store that. Actually, just so I don't have to actually take an x out of any particular data set. Now what I'll do is if I store what the dimension of the digit is, I can make just a dummy x. So just a dummy variable. I'll say x is equal to torch.zeros. So I'm going to make something that has a single batch, but just a dummy data, just to get my shapes right. So single batch, and the num channels in the input was actually 1 as well, and then the width and the height are the dimension of the digit. So now let me just send this tensor through. Oh, I didn't like that. Dim digit. Okay, so anyway, that's enough for me to get the shapes, which is all I need for now. So I'm going to make this little dummy thing. I'll remember the shape here. And so now I don't have to use magic numbers, because what I can do is I can have a linear layer going down from whatever this shape is. So I'll say product of, or maybe mp.prod. So multiplying that 128 by 2 by 2, I'm going to go from that dimension down to my latent dimension. All right, so finally, if I were to say x out equals linear x out dot shape, x out dot shape, what I would see is finally I'm down to 2 dimensions. Okay, but differently from how I did before with the multi-layer perceptron, I've actually sent myself through some convolutional layers. That's a little bit more powerful for image data specifically. So great, I've gotten down to 2 dimensions, and that's my latent space. Now I need to go back up to my original image resolution. So I need to undo everything I did in my decoder. All right, so first I just clean up the code a little bit, and now I'm going to start creating the decoder. So looking back at what we did before, we went down to the small dimension. Now we're going to start to go back up again. So the last thing we did was go down from some flattened layer to our latent dimension, and we want to do the same thing in reverse. So let me start anew with some layers here. And my first layer is going to go from, it's going to be a linear layer. It goes from the latent dimension up to that flattened shape there. And maybe I'll go ahead and follow that with the leaky ReLU. So it's going to go to the flattened shape. Now I want to unflatten it. So I want to shape, I know I have actually 512 dimensions. I know that's what this is in this case. I'm going to go up from 2 to 512 dimensions. And then I'm going to reshape those 512 dimensions into a 128 by 2 by 2 again. Now that's something I can remember. So I know if I send something through a batch dimension and just flat dimensions, what I'm saying is that next dimension, so dimension at index 1, needs to be reshaped to whatever this shape I remembered is. So let's see if that works here. If I were to say nn.sequential layers and I were to apply that to the encoder of x, it worked. Okay, so let's see. So good. So I've brought this up back from, so encoder brings it down to 2 dimensions as we see here, 1 batch. So actually, yeah, let me just print the shape there to remind us. So encoder shape is 1 batch 2 dimensions in this example. 1 batch 2 dimensions. It's going to bring that 1 batch 2 dimensions up to 128 by 2 by 2. Awesome. All right, so in the interest of time, I did this part myself ahead of time, and it's basically, again, just the reverse of what we did here. We're going to go up in resolution by a factor of 2 each time. We're going to go down by a factor of 2 in the number of channels, and then we'll finally output a single channel. Now, the one thing I did here that's a little bit different from what you might see from other people is there's this thing called conv2d transpose, which does the opposite of convolution, and you can upsample with it. I've had better experience in some of my applications doing an upsample first and then using an ordinary convolutional layer. So here I'm saying I want you to upsample by a factor of 2 and then just apply an ordinary convolutional layer to that with a stride of 1, so I'm not changing the resolution. So up the resolution by 2 and then just stride by 1. I don't know, I've had a better experience with that. You can avoid these things called checkerboard artifacts. But anyway, okay, so let me take a moment. I'm just going to put all of this, so this works, by the way. If I run this and then I'll say, I make my decoder, and then maybe I'll say x out is equal to decoder encoder x. That runs, but it's going to be complete garbage. So if I look at this, first batch, first channel, blah, blah. This should be, whoops, I got to detach it. Well, I guess it's not complete garbage. Well, it is, it's certainly not the digit I put in. Yeah, I guess because of the smoothing, it ends up not just being noise. But yeah, this is not the digit I put in. So I have some learning to do. So let me take a second to set up, I'll put this stuff I'll encapsulate this inside a class, and then I'll do the train loop and then show you how that goes. So give me a second to just reorganize this code a little bit. Nothing interesting here. I'm sure you could do it. So I'll just do it myself. All right, so just to show you what I did here, I inherited from this class nn.module to encapsulate everything in a class called conv autoencoder. I passed all the things I might want to vary to the constructor, like the depth, the dimension of the latent space, the dimension of the image I'm inputting, and the number of channels I'm inputting. Then I go ahead and made the encoder. That's pretty much exactly what we saw. The only thing I changed is I decided to make the activation in the latent space be a sigmoid, be a logistic function, just so I can compare it more easily to what I gave you on the assignment. Otherwise, it's exactly the same. And then I have a forward method. This is when you call the model, what you give it. And actually, I'm going to return 3 things here. The first thing is going to be, I'd like to return the encoding in the latent space. I also ultimately want to see the thing decoded. And then I'm going to compute the loss, which is the sum of the squared differences between the two, just like you did in the assignment. So pixel by pixel, I'm going to take the difference between what I inputted and what my encoder decoder says. And I'm going to square that and sum that up over all pixels. So I return those 3 pieces of information. Then I wrote a bunch of plotting code to help us watch the progress of this training. And then I set up a pretty standard training loop here using Atom Optimizer or all that stuff. I'm going to do it on my GPU so it's a bit faster. And then I got my standard training loop. And so, after 15 epochs, I got down to about 36 loss, which is actually kind of similar to what we did in the assignment. Just to show you how it progressed. Let me go back to the beginning here. So it started off like this, and as I trained, it got a little better. So here's the first epoch, and here's the last one. So you can see it's getting better. Still not perfect. I mean, comparing this to what we had in the assignment, it's not too different. So there's the one with the convolutional autoencoder, there's the one in the assignment. But this code that we've set up is very flexible, and it'll work much better on higher resolution images than what we have here. So I hope that kind of explains the convolutional layers and warms us up for what's to come.